Good morning, and thanks to the organizers for the opportunity. I am excited to be speaking to your community, and I hope we'll stay in touch. As Zach said at the beginning, I believe, partnership between nuclear physics and astrophysics, cosmology is increasingly important. Okay, let's move on. Okay. Well, first, a brief outline. First, to set the stage, some basic facts about neutron star that you all probably know way better than I do, but just to set the framework. The main body of the talk is about nuclear physics. I will introduce the most important nuclear physics concept and phenomena relevant for the structure of neutron stars. And those are neutron matter, I'll start with that. Neutron matter and its equational state, symmetric nuclear matter and its equational state, the closely related symmetry energy, and the paramount role its density dependence plays for stellar structure. When discussing predictions and constraints, I will emphasize the importance of ab initio versus phenomenology. This to be defined, I have visited later on. I will introduce the remarkable features that relate neutron star radii to the thickness of neutron skins, making a leap of tens and tens and tens and tens of orders of magnitude. Okay, now, well, neutron stars really are intriguing objects. For one thing, neutron star studies reach out to all the fundamental forces in nature. Also, they offer the opportunity to study matter under conditions not typically encountered in the laboratory. Weighing 1 billion tons per tablespoon, about the weight of Mount Everest, we cannot think really of an object of that weight. This is certainly no ordinary matter. And yet, these kinds of densities are everywhere around us, within us, in the form of tiny nuclei. Okay, moving on. Right, like I said, a few facts. Simply put, neutron stars are life after death of an ordinary star. Nuclear fusion, you see them schematically, is the mechanism that powers the stars. Before we develop a good understanding of nuclear physics and nuclear reactions, the question of what fuels our sun and stars was essentially unanswered. So when a massive, well, it has to be massive to get all the way to the end of the chain. So when a massive star fuses its way to the end, okay, that's iron. The fuel is gone. I'm simplifying everything here, okay. The iron core accumulates to about the famous limit of 1.4 masses. The electron, well, of course, the core resists the compression, giving up a violent shock waves that blows off the outer layers. The electron degeneracy pressure that was able to support the star against gravitational collapse is no longer able to do so. So collapse proceeds inward. At this point, protons and electrons find it energetically advantageous to form neutrinos in inverse beta decay. Escape, continue to escape forever, but obviously at the in a matter of few minutes, a neutrino escape in large amount, and the neutrons settle to become a neutron star with, and I say here at least, degeneracy, neutron degeneracy, pressure opposing gravity. In reality, well, neutron degeneracy can in fact support a lighter star, maybe 0.8 solar masses alone, but clearly the short range neutron-neutron interactions plays a major role, as we will see. And so what we just said basically was already said in 1933 with all reserve. With all reserve, we advanced the view, and so, etc., etc. 1933. Okay, so with 1 to 2, let's say, solar masses packed in a region the size of a city, typical density are comparable, like I said, to the central densities of atomic nuclei. About 10 to the 14th grams per, here it is, the typical size, 1 to 2 solar masses within, in an area that's the typical size of a US city. Okay, so typical densities, average densities are like that. Now, and the radius, okay, already commented on that, the greater Chicago area. Now, when I say in what follows, excuse me, when I say in what follows canonical mass neutron star, or the average mass, or the medium mass, I mean, average is not really the right thing, correct, but oftentimes I will say the canonical mass neutron star. So what I mean is the 1.4, approximately 1.4 solar masses. Okay. Right now, we are interested in the nuclear physics aspect, so let us focus on a senior neutron star that has recovered from its birth trauma, past the outer crust, the inner crust. There is the outer core, basically a fluid of neutrons, neutron-rich matter, that is where nuclear physics, nuclear theory can realistically make predictions. And then, well, let me go back to that. Can make prediction, which of course are at the quantum level. And this is the interesting transition, as Maria mentioned at the beginning, from quantum to, very, very, very large. Then there is the unknown, perhaps 10 times nuclear densities. I mean, it is unlikely that confined hadrons would exist in such an environment. So many scenarios have been advanced. Strange hadrons, kaon, condensate, phase transitions, particularly to quark, gluon, plasma, and others. But the fact is, we don't know for sure. We don't know. All right. So here, my role here is to address the question: what is the role of nuclear forces that so closely connect? Well, microphysics, yes, it's microphysics, but more like femtophysics to telescope physics. It's basically all in the main input of the Tolman, Oppenheimer, Volkov equations that you all know very well. These are the well-known non-linear differential equations to be solved for the pressure at some distance r from the center and the mass energy enclosed in a sphere of radius r for a static, spherically symmetric object in curved space. The first two terms here, well, this one is clearly the Newtonian limit. These first two correctional special relativistic correction, and they go to zero in non-relativistic limit. This object is a general relativistic correction. Aside from units here, you can recognize a potential. So is the increased potential, increased gravity in general relativity. This has an obvious meaning. Oh, let me complete the definitions here. Epsilon here is energy density, energy per volume, P is pressure. Given the EOS, sorry, I think I introduced the acronym before, equation of state, or EOS, versus density, and EOS, energy density versus pressure, they are integrated from the pressure outward until vanishing of the pressure signals the end of the star. And thus the radius, and therefore the radius where the pressure is zero and the total mass energy enclosed within that radius. So, okay, so the equation of state is where the nuclear physics is. Now we have to go a little bit more in depth. The simplest picture of the nucleus goes back to the semi-empirical mass formula, also known as the liquid drop model. Now, this is not how we do nuclear physics today, but it is important to give an intuitive picture of what we need. Its ability, so this is the formula, okay? I'll explain. Its ability to capture basic bulk features has never gone out of fashion in spite of its simplicity. The binding energy per nucleon that you see here, this is the binding energy per nucleon in a typical nucleus, is written in terms of just a handful of terms. They are inspired by the dependence of nuclear radii on the cubic root of the mass number A. Let me put the definition here. And so consequently, the definition of volume and surface and so on. The coefficients, A, V, A sim, and so on, are fitted to actual nuclei, of course, to the nuclear chart. Now, noting the sign convention, the binding energy for a bound system is positive. So only the first term, as you can see, provides attraction. All but the first, in fact, are, because they have a negative sign there, are destabilizing effects. So they take away from the binding energy. The first is a constant whose value is extracted to be about 15 to 16 MeV, and which represents the binding energy per nucleon in an infinite system of nucleons. There is no signature there of finite size or anything else. The second term, as you can see, that's the A sim, depends on this on the neutron proton asymmetry or relative neutron excess or isospin asymmetry, as we like to call it. Now note that the second term is the energy price. There is no better way to put it, is the energy price a nucleus has to pay for being asymmetric in terms of neutron proton concentration. Too many proton is not okay because there is too much Coulomb repulsion. Okay, then you go ahead and add neutrons. And yet, because neutrons don't bind, as we shall see later, you can add neutron up to a point, okay? And so that is why this term is in fact stabilizing. You can add neutrons up to a point, but not forever. That is why nuclei are so tiny and don't turn into neutron stars. Anyways, we will not, so let me just, we will not worry about the other terms because they depend. This is AS is a surface, AC is Coulomb, because they depend on the finite size of the nucleus, the Coulomb repulsion between protons, which is AC, and other small corrections because we won't worry about it because we are about to drop them, to send them away, going into some idealized infinite system. And by the way, apologies here, I should have, so nucleons that you see there is just a generic noun for either a proton or a neutron. So, okay. Great. So moving on to an infinite system of fermions. Let's see, an infinite, yes. Like I said, we have dropped unnecessary terms. So this is an infinite system of fermions acted on, I'm sorry, this was my finger, acted on by their mutual strong force and nothing else. The natural extension from before, and before is what you have here in the lower left corner for your recollection. The natural extension is to replace neutron, proton, and nucleon numbers with their respective densities, particles per volume. So now this is the isospin asymmetry parameter alpha in terms of this density ratio. The energy per nucleon in neutron-rich matter is then given by two terms, both of which are function of density. So, I mean, this and this. Now, if the model has to make any sense, the first, and meaning this one, should be about 15 to 16 MeV, like this, okay, at saturation density, where saturation density is basically the normal central density of most nuclei. And the second term, I lost my cursor, this function of rho here, should, for the same reason, be comparable, have a comparable value with this asym coefficient. This term here, which is a function of density, can be calculated at any density, is the symmetry energy, which will play a very important role of what comes next. Okay, so now allow me to regroup all the important facts and introduce also a slightly different notation. Apologies for that. So again, we call this object here the equation of state, the energy per particle in as a function of density rho and also isospin asymmetry alpha. And as this form, which we refer to as the parabolic form as a function of alpha. Alpha is, of course, a parameter that goes from 0 to 1. 0 means no asymmetry. 1 means this, means that when alpha is 1 here, you have pure neutron matter. When alpha is 0, you have symmetric nuclear matter with equal density of neutrons and protons. Okay, so now what, well, before I get to that, let me stay a moment. What does a theorist do? Well, they calculate, hopefully ab initio, where ab initio, parenthesis, okay, where ab initio means that you start with realistic free nucleon forces, free nucleon free space forces, and proceed into the many body system with no adjustable parameters. So you don't have parameter to fudge around, or this is what I do for oxygen, this is what I do for carbon, and so on and so forth. Nothing like that. So back to what I was saying, which I forgot what it was. Okay, so they calculate these equations of state in symmetric matter, in neutron matter, microscopically. The symmetry energy is easily extracted, as you can see, and then they apply them. They apply them wherever they want to. For the purpose, okay, so it is. Now, this is in general useful, but particularly for the experimentalists, phenomenologists who work on seeking empirical constraints for the various parameters of the symmetry energy. They find it useful to expand such said symmetry energy in a power series that you see here down about rho naught. So rho naught will be referred to as a saturation density or typical central densities of all nuclei. By doing so, they define coefficients with a particular physical significance. I mean, for instance, L, which is where the spotlight is going to be in a minute, is clearly proportional to the first derivative. Well, time 3 rho naught, okay, to the first derivative of the symmetry energy with respect to density or density slope, often referred to as the symmetry pressure. The derivative is a pressure, L as the dimension of an energy. So that being, let me see, yeah, that being said, let me tell you a little more about what the theorist actually does. Now, the problem of the nuclear force has engaged the best intellects for decades, and it's by no means a closed chapter. The current view today is that the best way to deal with the complexity of the nuclear force is to think in terms of scales and determine the appropriate degrees of freedom for a particular scale. So starting for, I don't know, the first one here, kind of a very rough view of this undefined object with some, it's a density functional, something like that. A sharper look reveals closely packed protons and neutrons in the typical raspberry-looking artistic impression of the nucleus. An even closer look opens the question of what keeps the protons and the neutrons together, which here, right here, is shown in the so-called traditional meson exchange picture. The pion is a meson, and the force has been traditionally described up to, you know, the 80s or so, even 90s, as a meson exchange force. And okay, so now what happens next? Well, sharpening your microscope even further, you learn about the substructure of hadrons. Nucleons are hadrons. So, and here you see, you know, the substructure with gluon, you know, created forces. So the question is, are nucleons and mesons the appropriate degrees of freedom or for nuclear physics, or should they be quarks and gluon? In other words, are you going to look, when you discuss the interaction or between these two objects here, are you going to take this approach? Or are you going to consider two objects of this kind, where obviously the quarks would be the degrees of freedom, okay? Well, effective field theories, effective field theory, I will say a few more words in a moment, says it depends on your resolution power. Namely, it depends on the energy. How much can you probe, what is unnecessary to retain as degrees of freedom, because your resolution power would not care about those. Okay, continuing on that, just a little bit. The general consensus, okay, today is that the so-called nuclear chiral effective field theory has become the most favorable approach to construct nuclear two, few, and many body problems, many body forces, excuse me, in a systematic way. In short, its strength is to have a firm connection with low energy QCD, quantum chromodynamics, the actual theory of strong interaction, by respecting the symmetries of QCD. While at the same time retaining the familiar degrees of freedom of low energy nuclear physics, which are nucleons and pions. Also prediction, as you will see, can be improved systematically thanks to an organizational scheme to rank order the various diagrams. So you can really control these forces, the onset of these forces in a controlled hierarchy. And well, obviously I won't stay much on this, but for the purpose of establishing the proper framework and also to introduce a notation, this is how 2, 3, and many force and many nuclear forces are constructed systematically. Note, these are just Feynman diagrams, okay? They are topologies, okay, which can be written out, although it's lengthy and tedious. Each order, which you see on the left, corresponds to a particular power of the expansion parameter defined with respect to an appropriate scale. Lambda, remember, it's an issue of scale, okay? Lambda, known as the chiral symmetry breaking scale. And at each order, the diagrams that one needs to include are consistent with that power of Q, are well defined, instead of the random approach of the meson exchange theory where everyone picked what is that they wanted to pick. So we speak of leading order and next to leading order and next to next, next to next to next, next to next to next to next. So obviously the exponents, obviously, unfortunately, the exponent notation was introduced for the record. Our predictions, we include all, first of all, high quality, high precision two-nucleon forces. There are more here, and all the three-nucleon forces that are supposed to appear at this order. Everything consistently at N3LO, which, by the way, is called the fourth order for technical reasons. Okay, so that's, and to the best of my knowledge, there is no complete calculations at N4LO at this time. Okay, so now, okay, ab initio prediction. So these are my predictions, my group prediction for the equation of state of neutron matter, the N, energy as a function of density, and then comes symmetric nuclear matter, energy as a function of density. I should mention, I on purpose left the other, but my latest calculation is the red in N3LO. So just look at the red if it makes it easier. You should, in fact, just look at the red. Of course, the symmetry energy, which has been, well, if you don't remember how it is defined, you can see it from here. So this is E0, this is 0 here. This object with alpha equal 1 is pure neutron matter equation of state, and then the symmetry energy. Okay. Now, yes, the striking difference between neutron matter and symmetric matter is that the energy per neutron in neutron matter is a monotone, as you can see, a monotone increasing function of density, whereas the energy per nucleon in symmetric nuclear matter has a clear minimum. Okay, so here minimum, nothing. Okay, clear minimum obviously means that there is an equilibrium density beyond which it would not be energetically favored to increase the density. Okay, and by the way, this explains, obviously, goes hand in hand. They are the two faces, you know, two faces of the same medal. Explains why central densities of all nuclei are approximately constant at some equilibrium value, which, not surprisingly, is the saturation density of symmetric nuclear matter, here indicated with this box. Not surprisingly, in fact. On the other hand, neutron matter, to put it in a simple way, has no bound states. In fact, neutrons don't bind at all. They don't form, but we do not have a neutron-neutron bound state. Nothing to do with Coulomb, obviously, which is also why the symmetry energy term, which I showed you in the original liquid drop mass formula, is a destabilizing, although necessary contribution. In other words, adding more neutron can just compensate things for a while, but you cannot do it forever. Neutrons do not bind. Whereas here you see the force between neutrons and protons is, as we say, a saturated force. And when a force is saturated, this is what it means. Okay, all right. Now, as mentioned earlier, speaking of the expansion in terms of powers of Q, chiral EFT, effective field theory, is a low energy theory, low momentum theory. And you see, when you have high densities, you have high Fermi momenta that goes, it's 1-to-1, and therefore typical momenta in your system will be high, too high for EFT. So the complete EOS is created by matching. There is always matching, by matching three contributions. Well, first of all, this is not nuclear. There is a subnuclear crustal. You need a crust. This is something I borrow from other groups. There are people who work on the crust. I'm not one of those people. Join with the microscopic part. This is the biggie. Now, beta equilibrium, sorry for not explaining that. Beta equilibrium means that we don't just use pure neutron matter. Instead, we impose energy minimization with the constraints of charge neutrality and baryon density conservation, which result in a small fraction, a small proton fraction, and of course, leptons. And then we have the high density region. So what happens there? So to complete the EOS, we match the microscopic part with piecewise polytropes. A polytrope is a simple function of this kind. Gamma is polytropic or adiabatic index. Alpha is a coefficient that obviously we can match imposing continuity with another piece and so on. But this is a polytrope, okay? And this is kind of a, I think, fun picture. This is a demo of the procedure. At the end of the microscopic predictions, we match a variety of polytropes within a range of the adiabatic index. And then again, at another matching point, as you can see, there is this fanning structure coming out. The range for gamma, of course, doesn't come out of the blues. It is suggested. We use as guideline information from the literature, such as investigations that have fitted a large number of existing equations of state with piecewise polytropes. The range I use is in fact 1.5 to 4.5, following guidelines from the literature, and where the low value of gamma, you know, for those low value, I will refer to as, I will speak of soft equation of state, the higher values of gamma. Okay, I cannot stress enough that this is not a theory, okay, but it will serve the purpose to probe the sensitive of the non-star to pretty much wild, certainly generous variations in the unknown region. And so I think I am okay now. Let's see. Yeah, the crust. Oh yes, crust by Chirally constrained. Remember the middle piece, but polytropic extension. They go into the TOV equation. Out comes mass, radius, and whatever you want. I should also mention that we apply additional constraints. Actually, most recently, I take as the maximum mass that an equation of state should be able to support as 2.01 solar masses. To the best of my knowledge, this is the lower limit that we have, the lower limit of the maximum result.
Francesca, sorry to interrupt, but we have 5 minutes left until we have to start the next speaker. So you're
okay.
Question time. So yeah, go ahead.
Okay, I'll try and pick up the pace. Okay, so, and the causality constraint. Okay, that the speed of sound be less than the speed of light in dense matter. Predictions. Okay. Expansion I showed before. Okay, there it is if you don't. These are my values for the symmetry energy and the saturation density, of course, and for the parameter L associated with the density slope of the symmetry energy saturation, and for the radius of the canonical neutron star. Now, which are free to, you should read as 12 plus or minus 1 kilometer, easier to remember. Now, the radius is quite sensitive to the density dependence of the symmetry energy around saturation, that is L. But almost insensitive, I won't have time to show that, to how the high density continuation is done. So now L is also, so there is a strong correlation here. L is strongly correlated also with another observable. Okay, obviously I will skip this. So to make our acquaintance with this other observable, we need to make a leap across, well, a few orders of magnitude and go into the nucleus. The typical shape of proton and neutron density profile in nuclei looks like this. This is neutron, that's larger, and proton density profiles in lead 208. This is a simple calculation with density, with Thomas Fermi density an appropriate parameter. Okay, now my point here is the skin, the neutron skin. This is the observable to which L is sensitive, but L is sensitive to the radius of the star, so everyone is sensitive to everyone else. Now, neutron skin is defined as the root mean square radii of the neutron and proton distribution, which and the skin being the other observable which we were looking for is okay, let me see, go back here for a moment. Yeah, let's keep that in mind. And now constraint and prediction. To the best of my knowledge, the most recent experiment which measured the neutron skin thickness of lead-208 is PREX-2. There used to be a PREX-1, PREX-2 in 2021. The acronym stands for Parity Radius Experiment because it exploits weak electron scattering, and weak means parity violating, pretty much the same as we have done with electron scattering to get proton density distribution, which we have done about since Rutherford. Okay, so here, and you shouldn't take this cartoon too seriously, this is a weak electron scattering. The electron couples with neutrons, not protons, via the weak interaction. Again, the acronym PREX, Parity Radius Experiment.
We have just 1 minute left.
Can I have a couple more? Can I have a few more?
I think we should be fair to all our speakers.
I understand. I got carried away as I often do. Okay, so my prediction for this for the skin are between 0.13 and 0.17. These are these are on the soft side. Let me put it this way. PREX value, J, and forgive me for the new notation, is nothing but is sim at rho 0. L is whatever you see. The skin is whatever you see. Remember, my value are about 30, 50, and say 0.15. They extract the radius to be at minimum at least 13 kilometers. These are among the realm of possibility of even remotely realistic possibility. These are the largest I've seen. The author themselves write what you can read here. These results challenges myriad of experiment, measurement, and theoretical prediction. These are the authors themselves. I would rather say myriad of experimental measurement and theoretical prediction challenge this result. This is a correlation. Let me put everything out here so you can see it. Are there predictions that agree with PREX results? You bet, but they are not predictions. They are phenomenological models. What you see here on the lower left corner is a correlation. The same has been done, can be done, and has been done for the radius of the star and L. This is what I have here on the vertical axis is the skin. As you can see, everything goes. Everything goes from L about 0 to L about 120. Much very clearly, PREX value can be fitted by this model, which are relativistic field model, known since a long time to be very hard, very stiff. And there you find values of L in the hundreds. On the other hand, this is S. It's not a skin, it's symmetry energy. Here you see, for instance, the energy density, symmetry energy parameterized by the numerous, only a few of the many numerous parameterization of Skerr model. So this is certainly not ab initio. I will put the conclusions here for you to read and keep this in mind. So this incredible connection is through the pressure. It's through the pressure that pushes neutrons out to form the skin in the nucleus, as well as determines the radius of the star. I put them here, the conclusions. From the theoretical standpoint, the road ahead is still bumpy. At the same time, I can only echo this author, Mann, in saying that the golden age of neutron star physics has arrived. Thank you for your patience. Stay in touch. If there is no time for question, please send a question and maybe we can start a broader conversation. Thank you very much.